So let me start today's lecture, and we are doing a new topic, entirely new topic today, linear transformations. So what are the linear transformations? These are just maps from one vector space to another. So you are taking vectors from a vector space V and mapping them into, so this is some vector space V and another one W. So you pick the vectors here and map to some vectors in W. Now this W can be V itself. So you can consider these kind of maps as well. So you take a vector here and map it to some other vector in the same space. So this would be, that this is just a map in general. That's what a map is. But linear maps are special. A map is called linear transformation if it satisfies this property. The property is related to some linearity, that if you take two vectors from your space V and make their arbitrary linear combination with any two numbers A and B, then this map of this vector should split. The vector in W you get from this transformation should be same as the vector you get by transforming V1 itself and multiplying it with A. So this guy lives in the space W. And since it's a vector space, so you can multiply this object with a number and you get a vector back in W. And this is also living in W. So you can multiply with B. And since both of these objects now live in W, so you can add them in W because you can add objects in vector spaces. So this whole thing lives in W. And what the linearity condition is saying, so this is true for all V1, V2 in V, and all real numbers. Any arbitrary linear combination in V should split like this. So if you have this property, then this is a vector space. This is a linear transformation. Now, just to note, well, let's first consider some example. If I take any vector V, define this linear transformation from, let's say, R2, let me do it from R3 to R2. And I'm defining it like this. This is an arbitrary element of R3. And under this linear transformation, this vector goes to this vector. Oh, sorry. This vector. Now we want to check if it's linear or not. So what you need to do, if I apply this linear transformation to take two vectors two arbitrary vectors in R3, multiply it with a number, so make a linear combination. This vector is just this one. Adding these in my R3, I get now I use this rule. The rule says add the first component to the second, and that would be your first component according to this definition which I have cooked up, would be your first component. So I get this thing. And the second component is you just pick the second component. And this is the vector you get in R2 according to the linear transformation I have made up. But this I can split. I can write it because I know how I add these vectors over here. I can write this same vector as x1 plus y1. I've taken a common, plus b x2 plus y2 and y2 here. This is the same vector. I have just split it up. But this I know, this is same if I apply the linear transformation on this object. This would be the result. Similarly, if I apply linear transformation on this vector in R3, this would be the result. So I have got this condition that if I apply linear transformation on this linear combination, I get this linear transformation splits in the way I want it. So that means this map is a linear transformation. Is a linear transformation. Let's check another example. Well, before going to an example, let's note something. Because of this definition of linear transformation, note the following. That if I have two vectors v1 and v2, linearity condition of transformation, this implies that if I just add two of them, then it should split. And if I scale a vector, then this should come out because this is equal to this same vector. I can write it as something like this. 1 times 0 vector. I can always add a 0 vector. And then I use the linearity. No, I don't want to write it. I write it as a 0 vector. And this I write as plus 0 time some arbitrary vector w. The 0 will kill it and make it 0. But now I use the linearity. So I get this. But whatever vector I get here, when I multiply it with 0, it becomes 0. These are the obvious rules in a vector space. So I get this back. So that means if you have a linear transformation, these simple properties of splitting and scaling, they hold. This was almost obvious. But actually, these two are enough to check if transformation is linear or not. So if transformation is linear, this happens, and if this happens, then the transformation is linear. Because instead of V1 and V2, so if I just assume these, start from these. So if I take, this is one vector, this is another vector. This property says that it should split like this. And then the second property says that the scalings should come out. B, it was B. But this was our original definition. So if either you can take these two properties or this combined property over here, this is like same. Now let's keep taking a few more examples. Let's take this example. I define from R2 to R. Remember, just numbers are also a vector space. It's a one-dimensional vector space. If we haven't discussed it before, let's just quickly discuss. If I take two objects, how do you check if something is a vector space? If I take two objects from this set, so what are these two objects? These are two numbers. And if I multiply them with arbitrary numbers, x, y, again, arbitrary numbers, with these objects, can I multiply them? Yes, multiplication is defined for numbers. And can I add them? Yes, addition is also defined for numbers. This is also back in the set because it's a number. So real numbers themselves are a vector space. And it's a one-dimensional vector space because I can take this one as basis and all the rest of the numbers, and if I take any number x, this is just x times 1. And we know that we can scale vectors, so I'm just scaling 1. So it's a one-dimensional vector space. So if I do the following, if I define a linear transformation by this, we have to check if it's linear or not. Let me just this time do with the two properties I discussed. So I take two of them. I know that how I add vectors in R2. So this gives me this. And now the rule says you just add the two components. This is my vector, this is my first component, this is my second component. So I just add them. But here I can collect them like this. And this I know would be same if I had done this linear transformation. And in the second instance, I have to check the scaling. If I take a vector, I don't need the ones now. Then this is just ax ay, and I'm transforming this according to my rule, which is this one. This is just ax is just this just a times. This is just, I can take a common, and this is just a times L of xy. So the scaling also holds. So it's a linear transformation. Let me just give you another example. This is also from R2 to R, and I define xy is equal to, under this linear transformation, it goes to x square plus y square. Now we take two of them, x2, y2. This is L applying on, this is my vector, and I'm applying this linear transformation on this. According to my rule, this goes to x1 plus x2 whole square plus y1 plus y2 whole square. So this is x1 square plus x2 square plus 2x1 x2 is 2y1 y2. But this is not equal to if I had applied this linear transformation on these individual ones, because this would have given me x1 square plus y1 square plus x2 square plus y2 square. This guy has these two extra terms, so they do not match. So these are not equal. So that means this transformation, this time I defined, is not linear. So you have kind of this obvious situation where you can tell if something is linear or not by, usually you just have a linear combination appearing in the formulas. If they are like squares or products, things like those, they always turn out to be having some problem with linearity. So that's why things having squares or multiplications, they are not called linear. Let me do some more examples. Well, first, let me give you just a terminology. This is called, so as I said, that you can consider maps from V to V, from same space to itself. If you do that, this is just called the linear operator. If it's linear, if this map is linear, linear operator on V. So for example, I can take that I take a V and I put it equal to 2V. So if I have a vector, I'm scaling it, making its length double. Now the question is it linear? We can easily check. If I take two vectors and make an arbitrary linear combination, it should split. Now, but I just apply the formula, this formula. It says multiply this vector by 2. But I know the rules of scalar multiplication, it splits over the sum on the vectors. And this is just a times 2v1, which is a formula which is the result of action of this linear operator on v1. And this is the result of action of linear operator on v2. So proves that this is linear. So scaling is linear. Another example, again in 2 dimension, I define this. The action is to change this vector to a0. So what is it doing? If I consider a vector, it has a x component, which is I'm writing as a. Well, let me write x and y. Would be more obvious. It has an x component and a y component. I remove the y component. I set the y component to 0. So that means I just get this vector having it equal in length as the x component of my original vector. So this thing you're projecting onto the x-axis. So this operator, you can think of it, since it's an operation on the vector space itself, it's an operator. We haven't checked if it's linear or not, but it's a projection operator. Takes the vectors in your vector space and projects them onto the x-axis. Just retains the x component and throws away the y component. So again, very easily can be checked. All you have to do is make this linear combination. And a y1 plus by2. So the rule says just retain the first and set the second component equal to 0. And this is just obviously equal to this. So it is linear. You can consider this transformation. What is it doing? You take a vector, you are retaining its x component as it is, but reversing the y component. So you can call it reflection through x-axis. And you can check very easily that it's linear. We can consider this transformation, that xy, an arbitrary vector goes to this vector. Y sine theta, x sine theta plus y cosine theta. This is rotation by, if you have this vector, you rotate it by an angle theta, the components of the new vectors will be given by this. This is rotation. And again, I'm not going to do it, but you can check it is linear. Let me give you another example of a transformation which is not linear. An operator on this vector space which is not linear. It takes this arbitrary vector to this one. Now, as soon as I see some kind of a product between these components, or a squaring, any product of these components, I should be ready to conclude that it's not going to be linear. So we can check if I take two of them, add, I know it should split, but let's see if it does or not. So when I apply my rule, I get this product of the upper and the lower component, and then minus x1 minus x2 plus y1 plus y2. So this is equal to x1 y1 plus x2 y2 plus x1 y2 plus x2 y1. And down here, so this, I could split them up, open them up, if these terms were not here. If these terms were not here. Because if I just take this, then it would be minus x1 plus y1 minus x2 plus y2. I cannot, this sum is not equal to this vector. I have to add some more. Maybe I can write it like this. This guy is already but I have this extra vector. So these two, this is not equal to, does not split, so not linear. Now we have said there's some very obvious extent properties of linear transformations. One is almost obvious, since we said that this splits, this splits, this implies actually that it splits on more than two as well. Because if I take a third one, I have a V, a W, and let's say an X. I can think of this as one vector, because when I add two vectors, I do get a vector. So take it as one vector. Let's call it U. And if it's linear, then I know that it must split on these two vectors. So it splits like this because of linearity. And but now I plug it back. So the u was this. And again, over here, it splits because of our definition of linearity. And there's this piece. So it splits on 3 and so on. You can include more. You can do it step by step and you will conclude. So you don't have to do step by step every time. Linearity is this general splitting. If your transformation is linear, this will happen. This is what you have. So very important. Splits over an arbitrary sum. And similarly, if you have minus v, then this minus will just come out because minus v is just minus v, 1 times v, which is minus 1 times, which is just minus lv. There's this property which is also kind of a quick check. It's not a sufficient condition for proving linearity, but it's necessary because so sometimes you just see and check if this is holding or not, and if it's not holding, then you know that your transformation is not linear. So what is that? If I take the zero vector, so I have a linear transformation from some v to w, a general. W could be same space or some other space. Then if I apply this linear transformation, so it first of all it's defined for all vectors in V. You cannot leave out anyone. All vectors, this has to be defined for all vectors. That's the part of definition. Now what is this property? It says that if I apply the linear transformation on the zero vector, then I must get the zero vector in the W space back. How do I prove it? Why it should be necessary? Because the zero vector, I can write it as 0 times an arbitrary vector in V. Now linearity demands that this 0 comes out. So I get some vector from the W, but it's being multiplied with 0. So it makes it a 0 vector. So that must happen. So in other words, you have V, you have W, you have a 0 here. Under the linear transformation must go to the 0 here. The 0 vector here must go to the 0 vector there. So let's, for example, take this example. Uh, we we took this one, that x1, x2, x3. Suppose I take this. Minus x3. I can check that if I take the 0, it does go to, I have to add the first component to the second and subtract the third from the second. So it does gives me the zero of, which is the zero of R2. Let's consider this transformation. I take this, well, let me write XYZ. And under this transformation, this goes to Z plus, so what is this? I can think of it as adding a fixed vector to all my vectors. There's some fixed vector. I have chosen 2, 3, 5. I take any other vector. I want to transform it. All I do is add this fixed vector to it and get this new vector. Addition of one vector to all. No, but if I apply it to the zero vector, what do I get? 0 plus 2, 0 plus 3, 0 plus 5. So I get 2, 3, 5, which is not 0. So that means it could not be, this could not be linear. And indeed, you can check that if I check it, if I check one of the linearity thing, let's check the scaling. So I'm applying this to this vector. According to the rule, this is ax plus 2, ay plus 3, az plus 5, and this should be equal to this thing. But this is equal to, sorry, x plus 2, x plus 3, y plus 3, z plus 5, and this is equal to ax plus 2a, ay plus 3a, az plus 5a. So not equal to this. So we confirmed that it's not linear, and it could not have been. We just, because it did not map 0 to the 0. Now, what else should we discuss? Yeah. Let me give you another very interesting example of linear transformations, or defining a linear transformation. Example, or maybe it should be considered a result, a kind of a theorem, that for every matrix, every m by n matrix, we can define a linear transformation from Rn to Rm by giving this definition, that V1, V2, Vn belonging to Rn goes to V1, V2, A1n, AM1, AMN. So just multiply this matrix with your V, and since A is m by n and V is n column, so we know that we can do that. And the result would be some m column vector. So we have defined a transformation. Using our matrix, take your matrix and take any vector in Rn, take this fixed matrix and start multiplying your vectors with this matrix. You start getting vectors in Rm, so you have defined a map for each vector in Rn, a vector in Rm. So it's a well-defined map, but the question is it linear? So very easily we can check. Like if I have A1n and I multiply this matrix with a sum, what will happen? I will have this matrix as it is, and I will have this sum. So when I will write the matrix product, I will get these kind of things. A11 times V1 plus U1 plus A12 into V2 plus U2 and so on. This would be the first element. Now, since I know how the matrices are added, I can split them up, split them open. And I will have A11 V11 plus A12 A11 V1 A12 V2. So in one matrix I retain these and I split, and in the other matrix I retain the U1 guys and so on. So this is just A acting on these V's. And this is just A acting on U's. So it splits. And similarly, you can check scaling. I can do it much more efficiently. I just wanted to show you the idea, but we can use our index notation, and that would be very helpful. So I am applying, I take these two vectors and I apply A and I get some W. These W's, jth component, well, let's say ith component, we know how we're going to write it. It would be I, j, and the jth component of this vector, sum over j. But this just splits open. I can split these sums like this, and this is just the ith component This by definition is the ith component of A acting on U, and this is by definition on V, and this is by definition the ith component of A acting on U. But we started from here. This was the ith component of A acting on U plus V. So the components match, it means they're same vector. So this action of A matrix product does split on these vectors. And similarly, you can check scaling. I could have probably included over here. All I would have got these guys, and you get the full linearity. So matrix product over the vectors is linear. So given a matrix, you can define a linear transformation. What is more interesting is that given a linear transformation, you can define a matrix, what we call a matrix representation of this. Matrix representation of the linear transformation. So what is this matrix representation of a linear transformation? So if you're given any linear transformation, let's say from Rn to Rm, for now I'm defining it, I'm considering those linear transformations which are from Rn to Rm. But since we studied that we can translate any n-dimensional vector space and map it to Rn, and take any other vector space, m-dimensional vector space, and map it to Rm. So this would actually be true for any finite dimensional vector spaces. That with any linear transformation on any vector spaces, you can associate a matrix. But for now, let's, for clarity, look at the situation when you are going from Rn to Rm. So what does, let's say this is a theorem. For any linear transformation like that, there is a matrix. Matrix m by n such that the action of this linear transformation on your vector in Rn is equal to just applying this matrix on this vector. For every V in your Rn. And we also know that what this matrix would be. This matrix is just given by linear transformation on the basis vectors, the standard basis vectors. Take the standard basis vectors, make the get the new vectors, and make your columns of A through those vectors. So how do we see it? So let's start by defining AI ith vector as the linear transformation of the ith standard basis vector. Just for reminder, these are these guys. That the ith place, at the ith place you have a 1 and all the rest are 0. You take these guys and start transforming by applying your linear transformation, whatever your rule is. You get some new columns and you collect those columns in a matrix, and that matrix will do the job. So define this and let A equal to this matrix. Now I have to check the action on any arbitrary V. Any arbitrary V, this is again just a reminder, is like that, which is actually equal to, we can think of it like this, that these are these components are the coefficients in the expansion in your standard basis. So this is just V1 E1 plus V2 E2 plus Vn En. Then if I apply L on V, what is the effect? Well, whatever the effect is, I know that by linearity, it has to split. So I'm applying it on this expansion because V is equal to this expansion. And because of linearity, it must split. So it splits, but you know that what is this guy? You know that if you are given a matrix, made up of these columns, each column, because each L takes this n dimensional column E1 or E2 or E3 into a m component column. So these, you have n columns and each has m components. So this is a m by n matrix. And you are multiplying it with V1, V2, Vn. Because we know that one way to multiply the matrix with a vector is to make the linear combination of the columns of the matrix with the components of the column with which you are multiplying it. So this is equal to this. But what is this? That's exactly what we wanted to prove. That you have a matrix like this whose effect when you multiply it on your vector is same as the effect of linear transformation on the vector. So let's again take some examples of this. So suppose I consider this transformation. This is actually rotation by 90 degrees. If you have this goes to this. So in any case, this is a linear transformation, and we want to find the matrix representation of it. So very easy. All you have to do it on the standard basis. So 1 0 goes to 0. The rule says that this comes here with a minus, and this comes down here. And on the second vector, You have a -1, and this comes down here. So the matrix of linear transformation, for now I'm writing it like this, but later on I'll just represent them again with an L, is you collect these, the transformed basis vectors. You take the basis vectors, the standard basis vectors, transform them, and collect them in a matrix in the same order. Remember, you have the ordered basis, so in the same order you collect them. So this is the matrix. We can check if it does the job for us. So if I apply this matrix on an arbitrary vector, what does the matrix product gives me? 0 times x0 minus y, 1 times x plus 0 x, which is correct, which is what I wanted. So we had discussed this example. Let's take, this was from R2 to R2, but as we have seen, doesn't have to be same dimensional space. Let's take this example from R2, R3 to R2. To compute the matrix, all you have to do is apply this transformation on the basis vectors. So when you do it on it, x plus y gives you a 1, y minus z gives you a 0. On the second basis vector, x minus y 0, x plus y 0 plus 1 gives you a 1, and then y minus z is 1 minus 0 gives you a 1. And the third one, x plus y gives you a 0, y minus z gives you a -1. So the matrix of this transformation is just collect these guys. And again, we can check if I apply it to an arbitrary vector in R3, what do I get? Matrix product gives me 1 into x plus 1 into y plus 0 into z. X plus y, and 0 times x, 1 times y minus 1 times z, which is what you wanted. But by the way, this gives us another very important idea. Very important. Since I can write any vector, expand it any vector in a basis, I don't even have to take the standard basis. Let's say this is a basis. It's an n-dimensional vector space, so you have this basis. And v1, v2 are the coefficients, because I know I can write my vector as a linear combination in a unique way in terms of an expansion of basis vectors. That's the whole point of having a basis. And v1, v2, vn are just happen to be the components or the coefficients of this vector in this basis. Now, if I want to compute, I have like trillions, not trillions, infinite number of vectors. And I want to give a rule, or I want to know how does this linear transformation X on it. But actually, if I apply a linear transformation to an arbitrary vector like this, because of linearity, these coefficients come out, and if I just knew that how does this linear transformation X on the basis vectors, I can then compute its action on an arbitrary vector. Because all I will have to do is make this linear combination. So it is enough to define the action of linear transformation on a basis to completely specify it. If you know it on one basis, you know the linear transformation completely. So for example, if I have this basis in geometrical vectors, and I say my linear transformation takes I to j, j to k plus I, and k to minus I. Then if I am given any vector xi plus yj plus zk, and I want to apply L, I know what will happen. Let's take a concrete example. 3i minus 4j plus 2k. So 3 comes out, I goes to j. Minus 4 comes out, and j goes to k plus I. And 2 comes out, and k goes to minus I. So I get, if I now start collecting these, minus 6i plus 3j minus 4k. So I know then, where does this vector go? This goes to this vector. And I got it just because I knew what's the action of the linear transformation on the basis vectors. So let me take another example. Well, let me give you kind of an example of a linear transformation. Another example of a linear transformation. You have this P4 polynomials of degree 3. This is the notation the book is using. P3, because polynomials of degree 3 have dimension, this vector space has dimension 4. That's why they're writing it as P4. P3 are polynomials of degree 2. I can define a linear transformation from P4 to P3 to a derivative. Let's define it, that P of x goes to P derivative of x. So for any P4 living here, you will get another polynomial which will be living in P3. So what's the basis over here in P4? In P4, I can take this basis. This is the standard basis. And in P3, I can take this basis. Now let's compute I know that if I'm given uh, any polynomial in P4, I can collect these coefficients. So this is the expansion in the basis and write them as this. So this is the representation of this polynomial in the standard basis. Then, and similarly anything here, bx square, b1, b2 x2 plus b1 x1 plus b0 times 1, I can write it as b naught. So in other words, first of all, if I define it this way, is it a linear transformation? Is derivative a linear transformation? So if I'm given two polynomials, you know how do you differentiate it? D by dx, I can even multiply them with some constants. The rules of derivative are linear. The derivative splits like that. So derivation is a linear operator. Is a linear transformation. So what would be the matrix of this derivation? Because it's a linear transformation, so I should be able to construct a matrix. So again, we take the rule that on the standard basis, my E1, so if I order the basis this way, I call that E1 is x3, E2 is x2, E1 is x, and E0 E3 is this, and E4 is 1. Then what is the effect of D on E1? Is the derivative of x3, which is 3x squared. So it's 3 times, if I call, similarly this guy has this basis, I can call them with same names. So it's 3e2 de2 x squared is 2x squared, 2x, so it's 2e1, and de1 is d by dx of x, this is just 1, so 1e0, and d of e0, so 1 is just 0, so 0 vector. So that means that my d of e1, I have to collect all these vectors. So the first one is 3, this is just 3, and then I don't have other things over here. So it's 3 0 0. Effect of d on e2 is 0 2 0. Effect of d on e1 is this vector, and d of e0 is just the 0 vector. So if I differentiate this polynomial, so what I'm doing is multiplying this matrix to this guy. And you can see you get 15 minus 6, 2, and that's it. And that's exactly, if you take the derivative, that's you get. This is a part of P3, P2, P3. Mm, I think we are running out of time. So let's stop here. I'm gonna send you all the stuff which I had promised I couldn't send yesterday, but I'm just gonna send you very soon, shortly, and make some more announcements as well. I just want to say, I mean, some students ask that the homework looks very long and how would they do it in 1 week? It's not very long. It just has lots of words, but solution is very, very simple. It looks long because it has explanations. So please start trying it, and I'm sending another one. So there is some message. Yeah, so people have asked me to extend the deadline. I'm gonna do it this time because I know people are lagging behind. But the issue is like you are just piling up work if it keeps happening. So I'm gonna extend it this time and probably then extend the next one as well. But you have to slowly start catching up. I know that people are behind, but people have to start catching up because at some point we have to finish the course, and you have to take the final. So please start catching up so that slowly, as we reach the middle of December, everyone has finished all the homeworks. So I'm just gonna give you some time to complete the work because of the situation we are in, but please start catching up. Okay. So I'll send the email about extension as well very soon, today at some point.